Hello. If you're watching this video, I assume that you are a student that is registered in Physics 328 or Advanced Mechanics. So here we are in a unique situation where we're trying to transition from traditional face-to-face lectures to something that is online only. So what I will attempt to do is to create these YouTube videos that you can access and watch whenever you find it to be most convenient. And so we're trying to put this together with basically very little notice and no outside support. So I'm going to do the best I can, and I hope that you'll be patient, and maybe in the end we'll find a solution that works reasonably well. So I will try to focus these videos on the actual physics from the course, and any sort of announcements about details about how the course is going to run from here on and so on will be posted to the course website. So please check the website frequently to see if there's any important updates. The URL, as you likely already know, is people.oak.ubc.ca/J Bobowski and then PHYS 328.html. So what I want to try to focus on today is from the textbook. It's section 11.6, so it's 11.6 from the Merriam and Thornton text. And the topic is going to be the inertia tensor for different coordinate systems. Specifically, what we might be interested in is, suppose that we have some rigid body and we selected some origin O. What we've talked about in previous classes is that we could, if we had some coordinate system associated with origin O, we could calculate a rotational inertia tensor, and then if we had some unit vector n hat that specified some direction through origin O, then we could calculate the rotational inertia for rotations about an axis parallel to n hat or along n hat. So the question is going to be, so what if we did that for point O? Could we somehow use the information in the tensor, the rotational inertia tensor for point O? Could we use that information then to say, well, what would the rotational inertia tensor look like for some other different point, Q, that is, say, translated with respect to point O? So we've previously found that if we know the inertia tensor, and in our notation we use curly bracket, for a body with respect to O, then we can find the rotational inertia for axes through origin via... so let's use the following notation. Say the rotational inertia for an axis along the direction of n hat would be equal to the following n hat dot with the rotational inertia tensor dot n hat. And so here we would use a row vector for this first n hat factor. This would be a column vector, and this we could represent as a square matrix. And so when you do that matrix multiplication, you just get a single number out, and that represents the rotational inertia about an axis in the direction of n. So just as a reminder, this n hat unit vector was expressed as cos phi 1 I hat plus cos phi 2 j hat plus cos phi 3 k hat. And so phi 1 is an angle between n hat and the x-axis, phi 2 is an angle between n hat and the y-axis, and phi 3 is the angle between n hat and the z-axis. So this n hat, what it does is it specifies the direction of the rotation axis. Okay, another thing that I'll just remind you of is that we had a general way of writing down the components of the rotational inertia tensor. So the components of I were given by, let's see, so we need two indices because it's a square matrix, so we need a row index and a column index, and the general expression was a sum over alpha, where the sum is going to go from 1 to n, where we imagine we have, say, n point masses, each with a mass, say, m alpha, that make up whatever our complete rigid body is. Okay, and then that was all multiplied by the delta function, delta ij, and then we're going to have a sum over k. The sum over k is the sum over components of a vector. And so x alpha k squared is, so if k equals 1, that's the x position of mass alpha. If k equals 2, that's the y position of mass m alpha. And if k equals 3, that's the z coordinate of mass m alpha. Okay, and then the other thing was we had x alpha I times x alpha j with a minus sign. Okay, so now let's get back to the original question. That's everything we so far know. What if we knew all of that for point O? Could we somehow use that information to determine the inertia tensor for point Q? So what if we want to know So I'm going to write the rotational inertia tensor with respect to origin Q as J with respect to point Q. Can we use what we know about I with respect to origin O to determine the elements of J? So if you think back to when we were just thinking of the rotation of say a slab or a plane-like object where the rotation axis was perpendicular to the plane, we made use of this parallel axis theorem quite a bit. So what we're really trying to do is we're trying to construct something that will be analogous to the parallel axis theorem. And so let me remind you what the parallel axis theorem said. So let's imagine we have some rigid body, and let's just suppose that this point is the center of mass of that body. And what we could do is we could calculate the rotational inertia about this axis through the center of mass. And we'll say that this body has some, that body has some total mass m. Okay, so this is the total mass. Okay, and what the parallel axis theorem allowed us to do was to take any axis parallel to I center of mass, and so let's say that that's some point Q, and then we could calculate IQ. Let's to be consistent with the notation above, let's say that we wanted the rotational inertia about Q, and we're going to call that J. Okay, what the parallel axis theorem said was that the rotational inertia about J could be calculated from the rotational inertia about the center of mass plus m times the perpendicular distance, say d, between those two parallel axes. And so if we knew that distance, then the rotational inertia about J was equal to the rotational inertia about the center of mass plus m times d squared. Okay, so it will turn out that if in the picture above we select the point O to correspond to the center of mass of the body, then we can generalize this parallel axis theorem for rotational inertia tensors. Okay, and so that's the first job. So let's see if we can draw first a picture. So what we're going to imagine is that we have some set of coordinates with an origin Q. And I'm going to call these axes capital X. So there's a component 1 in the x direction, component 2 in the y direction, and component 3 in the z direction. And then what we're going to do is we're going to have another origin O, and this origin will correspond to the center of mass of our body. And it's going to have its own set of axes, and we're going to call those axes little x1, little x2, and little x3. Okay. The vector that connects the origin Q to the origin O is going to be vector A, and that's a constant. Okay. And so what we imagine that we do is we have a vector from the origin Q out to some mass m alpha. So I haven't drawn it, but we're going to imagine that these two coordinate systems are within like some big rigid body. And so m alpha is one of the particles, one particle in the rigid body with mass m alpha. And so this red vector is capital R alpha. And then, of course, there's a vector from the origin O to that same piece of mass, and we'll call that little r alpha. So what we're going to do is we're going to suppose that we have determined the rotational inertia tensor for the point O. And so we're going to write the elements of the inertia tensor, say J, O. The inertia tensor J with respect to origin Q. And let's just emphasize that this is not the center of mass. We're going to assume that the point O is at the center of mass. Okay, so this, eventually it'll be important that O is at the center of mass. Maybe I should draw that blue to be consistent with that blue vector, little r alpha. So center of mass. Okay, so let's just write down the components of the elements of the rotational inertia tensor J. So it's a sum of m alpha, and then there was a delta ij, and it was a sum of k, and so now we have to use our big x symbols, right? Because we're now working with respect to the coordinate system with origin Q. And so this is just exactly what we wrote down in our little review at the beginning. I've just made the coordinates in terms of capital X's for coordinate system with origin Q. Now, from the picture above, there's clearly a relationship between the coordinates of big R and the coordinates of little r. And they're connected via this vector A. Okay, and so before I get rid of this picture, let's just notice that if we take A plus little r, that produces the vector big R. So we can relate the coordinates of point mass m alpha in the two coordinate systems via r alpha is equal to A plus little r alpha. And in component form, the equivalent expression is whoops, what happened there? So the equivalent expression is x alpha I, so ith component, I is 1, is the x component, I is 2 is the y component, I is 3 is the z component, is equal to the ith component of A plus the ith component of little r alpha. So I can be 1, 2, or 3. Okay, so all we're going to do is wherever we see a big X in this expression above, we're going to substitute A plus little r. Sorry, I really wanted that to be A plus little x. All right. So what do we get when we do that? It'll be a little bit of a complicated expression, but it's going to simplify quite a bit before we're done. So we get Jij is equal to the sum of alpha m alpha. Okay, so the first thing we have is a delta ij, and then we have the sum of k, and we have big X squared. So I'm going to write that as little x plus a, and this is a sum over k, so we take the kth components and then we square it. And we're going to do the same thing for minus the product of x times x. So we're going to get minus little x I plus ai times little x alpha j plus aj. And then we close our bracket. Okay, so we're just going to expand both of these terms. So what we end up with is sum of alpha m alpha and delta ij. And let's see, we'll get a sum of k x alpha k squared. So when I square x alpha plus ak, we'll get one of the terms will be x alpha squared. If we now jump to the second term, what we'll end up with is a minus x alpha I times x alpha j. And so that's the one I want to write next. So we'll end up with a minus x alpha I x alpha j. All right. And there's still lots of stuff left. Sum of m alpha, delta ij, sum of k. So we still have an ak squared that we didn't write down. So we get an ak squared. And we still have a cross term, 2ak times x alpha k. So we should get a plus 2ak x alpha k. All right, and then minus, so we'll have an ai x alpha j. So we should end up with an ai x alpha j, and there should be a j, oh, sorry. So where were we? We were doing an aj x alpha I, and then we should have ai times aj. All right, and then I think that's everything. But if we look at this first expression, the reason we separated the terms out in this way is because here, those are just exactly the elements of the rotational inertia tensor with respect to origin O. And so that's ij. Okay, so what we have so far then is jij is equal to iij plus the sum of alpha m alpha, delta ij, the sum of k, and we have ak squared minus. Okay, so now I'm going to reorder terms again. And so, in fact, I'm going to get rid of this. I'm going to keep the ak squared there. So that's that term. And then I'm going to write the minus aiaj term. So we get minus aiaj. Plus sum of alpha m alpha. So we have a 2 delta ij ak x alpha k. So we have 2 delta ij sum of k ak x alpha k. All right, and then we have an ai x alpha j and an aj x alpha I, and then that should be everything. So let's see if we can squeeze that in. Minus ai x alpha j minus aj x alpha I. So this looks like a pretty daunting expression, but it's going to turn out that everything in the second sum is going to vanish. This whole thing will be equal to 0, and let's try to understand that. So we start by considering the m alpha ai x alpha j term. So ai is just a constant. It just connects origin Q to origin O, and so it has no alpha dependence, so I can take that outside the sum. So I pull that outside the sum, and we have the sum of m alpha times the jth component of x alpha. But recall the definition of the center of mass coordinates. So the jth component of the center of mass is equal to 1 over the total mass times the sum of alpha m alpha x alpha j. The sum that we have over here is equivalent to this sum in the center of mass, and so if we just multiply by the total mass, m, then we get, I should label this, let's label this properly as the jth component of the center of mass coordinate. So then this would be m times x center of mass j. Okay, so let's just quickly go back and look at our picture here, way back here, and we made the assumption that we were going to choose the origin O to be the location of the center of mass. And if that's the case, then the lowercase coordinates, small x1, small x2, small x3, they're all measured with respect to the center of mass position. And so what the sum is really asking is find the center of mass coordinate relative to the center of mass origin, and of course that's going to be equal to 0. So if we take origin O to be at the center of mass of our body, then the sum of alpha m alpha x alpha j will be equal to 0. And this is because the jth component of the center of mass measured relative to the center of mass is just nothing. It's just 0. Okay, and so this is 0 for all j equal 1, 2, and 3. So what we've considered is this term in our sum. So if we distribute the sum over alpha and evaluate that sum, that would be 0. The second term is exactly the same. So that one's going to vanish as well. Okay, so let's consider the first term in the second sum, the one with the delta function. Okay, so we next consider the first term in the second sum. I'll rewrite it. So there was a 2 and a delta ij. So if we go back and look, 2 delta ij, there's no k subscript on the 2 delta ij, so I can pull it outside the alpha sum. So then we're going to have the sum over alpha m alpha, and then we have a sum over k of ak x alpha k. Okay, so that's the whole thing. Again, I can reorder the sums if I like. So we could write this as 2 delta ij, and then let's write the sum over k and put ak over here. And then we have the sum of alpha m alpha x alpha k. Well, now this is exactly like what we just did above over here. And we could say this sum corresponds to whatever the total mass of the body is times the, I just realized this should be a k, times the kth component of the center of mass. So this should be x center of mass, and whatever the kth component is. And again, we're asking essentially, where is the center of mass relative to the center of mass position? And the answer is 0. And so that means if we go back to here, we also can just throw away the first term in the second sum. And then the whole thing vanishes. And we're left with a relatively simple result that we get the elements of the J inertia tensor are equal to the elements of the I inertia tensor, and it's just whatever that first term was, and what it was a sum over alpha m alpha delta ij sum of k a k squared minus ai aj. Okay, So we can re-express the sum of k ak squared as these are just summing over the components of the A vector that connects origin Q to origin O, and so it's going to be A1 squared plus A2 squared plus A3 squared, which is just the square of the length of that vector, right? And so this is the x component, this is the y component, and this is the z component. Okay, the other thing that we have here is a sum over alpha, m alpha, and notice that inside the brackets there is no alpha index, and so the sum only operates on the m alpha. So we can write the sum of alpha m alpha is just adding up all the little bits of mass in our rigid body, and so that's just m, the total mass of the rigid body. Okay, so making those replacements then, we could write that, let's do it this way. We'll write the components of the I inertia tensor are equal to the components of the J inertia tensor, and then we have to subtract off the sum of alpha m alpha, which is just the total mass, and then we have the sum of k ak squared, which is a squared, that multiplies the delta function, and then we're left with ai aj. And so this is the generalization of the parallel axis theorem. For the inertia tensor. Okay, let's just remind ourselves that this has to be with respect to an origin O that's at the center of mass. So this is with respect to origin O at the center of mass of our body. And this one is with respect to any other origin, Q. Okay, so let's see if we can put this into practice with an example. And the example that I want to start with is one that we worked on in our last class. So example, what we did in the last class is we found the inertia tensor for a square slab with an origin Q at one corner. So what that looked like is we had an x-axis and a y-axis, and then we had a square. In the last class we said the squares had sides of length A. Here I'm going to use B. The reason I'm switching from an A to a B is because when we apply this generalized parallel axis theorem, A is going to refer to the distance from one origin to the center of mass. And so here, for the problem that we did, we chose an origin Q at this corner, at the bottom left corner. And we actually calculated all the components of this inertia tensor. And what we found was that there was an mb squared, and then we had a 1/3, a minus a quarter, 0. Remember, it was symmetric. So the 1, 2 element is the same as the 2, 1 element. Then 0, 0, 2/3. So that was what we calculated last time. Okay. So if we want to make use of this generalized parallel axis theorem, we have to locate the center of mass. And so it's obviously right in the middle of our square slab if it's a uniform slab. And then the distance, say along y, to the center of mass is half the length b, and likewise it's 1/2 of b along the x-axis. So if we were to write our a vector, what it would be is a b by 2 in the I hat direction and in the j hat direction. What we're going to need is the value of a squared. And so a squared we could evaluate as, say, a dot a. And so we'll get a b squared over 4 out front, and then I hat plus j hat dot I hat plus j hat, well, we'll evaluate to 2, and we'll get a b squared over 2. Okay, the other thing that it will be useful to do is to write out the components, the individual components of this a vector. So the x component, a1, is just b by 2. The y component, a2, is also b by 2. And then the z component, well, there is no z component for our planar slab, and so a3 is equal to 0. Okay, so we now want to apply our parallel axis theorem. And so what I'll do is, let's see if we can keep all of the important information on the screen. I'm going to rewrite this parallel axis theorem. So what it looked like was the elements with respect to an origin at the center of mass were equal to the elements at some other origin minus m a squared delta ij minus delta aiaj. Okay, but we've already worked out that a squared for our square slab is b squared over 2. So this is going to be jij minus m b squared over 2 delta ij minus aiaj. And so let's just go through the elements one at a time. So the 1, 1 is equal to j11, and j11 is 1/3 mb squared. So we get a 1/3 mb squared minus m, and the delta ij becomes delta 11, which is just 1, and then we get minus a1, which was b by 2, minus a2, which is also b by 2, and so this becomes 1/3 mb squared minus mb squared, And so what do we have? We have 1/2 minus 1/4, which is plus 1/4. And so this is mb squared 1/3 minus 1/4, which is mb squared, let's see, over 12. So we'd get 4 minus 3. Yeah, okay. So we get I11 is mb squared over 12. Okay, so that's the first element of our rotational inertia tensor with respect to the center of mass origin. If you did the I22 case, you're going to get exactly the same results, because if you go and look and you see the 1,1 element of J is exactly the same as the 2,2 element, and the 2,2 is going to involve A2s, which is B over 2, which is exactly the same as A1, which was B over 2. So there'll be no difference, and you'll get exactly the same results. Okay. Let's do the last diagonal element, I33. In this case, J33 was 2/3 mb squared, and then we have minus m, and we had a squared delta ij, and that delta ij is going to be a delta 33, which is going to be 1, and so we just get a squared times 1, which is b squared over 2. And then we're going to have minus a3 times a3 if we have the 3,3 element. But a3 we've already determined is 0. So over here we'll get minus 0. And when we combine everything, we'll get, let's see, mb squared 2/3 minus 1/2, which is mb squared over 6, and then I guess that's a 4 minus 3. Right, and then I33 just becomes mb squared over 6. Oh no. So we have mb squared over... Okay, so let's see if we can power through and get this finished. All right, so now we have off diagonals to do. So for example, I12. Okay, so we have to go all the way back here and look at the 1, 2 element of J, and so that's minus 1/4 mb squared. So we're going to have minus 1/4 mb squared. And it's going to be minus m, and then we're going to get a delta ij. But in this case, I is 1 and j is 2, and so the delta ij is going to be equal to 0. Okay, so we get 0 minus ai aj. A1 is going to be b over 2, and then a2 is b over 2, so we get b squared over 4. So we get b over 2, b over 2. And if you look at this, we have minus 1/4 mb squared, and then we have a minus sign and a minus sign. It's going to be a plus 1/4 mb squared. And when you evaluate this, you're going to get exactly 0. Okay, the inertia tensor is symmetric, so what we found is that I12 is equal to I21 is equal to 0. Okay, that's interesting. Let's do the 1,3 case. J13 was equal to 0. Okay, and then we get minus m. Delta 13 would be 0. So we'd get 0 minus, and then we'd get a1, which is b over 2, times a3, which is 0, because this is a planar object, and we would just end up with 0. And so we would get I13 is equal to I31 is equal to 0. Okay, the last elements that we have to do are the 2, 3 elements. I23. If you go back and look at the J inertia tensor, the 2, 3 element was 0, and then we would have minus m. We'd have delta 2, 3, which is 0, minus a2, which would be b over 2, times a3, which would be 0, and we'd get 0 once again. And we get this interesting result that all of the off-diagonal elements vanished. So we have, in all 3 of these cases, the off-diagonal elements all vanish. So all off-diagonal elements vanish. In other words, what we have is a diagonal inertia tensor. And if we enter in all of the elements, we get I is mb squared, and then we had 1/12, and then no off-diagonal elements, and then for the 2, 2 we had 1/12, no off-diagonals, and for the 3, 3 we had 1/6. We could, if we wanted, write this as mb squared over 6, 1/2, 0, 0, 0, 1/2, 0, 0, 0, 1. So this is a diagonal moment of inertia tensor. So the last thing I want to try to do in this video is to try to convince you that it's actually quite convenient to have a diagonal rotational inertia tensor, because it's going to make all of the calculations we have to do, calculations like angular momentum and rotational inertia, quite a bit simpler. So the next topic is principal axes of a rigid body. And so my first claim, I think my screen is frozen here. So I'm going to see, I don't want to stop the video. I'm going to see if I can get this to come back. And if I can't, I'll stop it here. Oh, that's such. Okay, here we go. I think this will reload the thing. Okay, so let's see if we can find where we were here. Okay, here we go. So, oh, son of a bitch. Okay, it is always possible to find a coordinate system for which the rotational inertia tensor is diagonal. This can be done for any choice of origin Q. Q could correspond to the center of mass of the body, but it doesn't have to. Q could be the center of mass of the body, but it does not have to be. And there's good reason for us to want to do this. It is very convenient to work with a diagonal inertia tensor because the expressions for things like angular momentum and rotational kinetic energy, which in general are complicated, become much simpler. So what we're talking about here is picking some point Q, and we have some freedom in selecting the orientation of our axes. We're going to pick 3 mutually perpendicular axes, but we get to choose their orientation. And if we can select the orientation such that the rotational inertia tensor becomes diagonal, it's going to make our calculations much cleaner and quicker to work with. So if we can select that set of axes, so the axes with origin Q for which I becomes diagonal, then these axes are called the principal axes. We're going to use a standard notation where we'll define some unit vectors. They're going to be E1 hat, E2 hat, and E3 hat, and we're going to choose those unit vectors to point along the principal axes. So let's denote E1 hat, E2 hat, and E3 hat as unit vectors along the 3 principal axes. Okay, so let's imagine that we've done that like we just did for the square slab with an origin at the center of mass. Then when we write down the inertia tensor, it has just 3 elements. And we could imagine trying to rotate our body about some arbitrary direction with an axis that passes through whatever origin we're working with, and we could write the components of that angular velocity in terms of these unit vectors E1, E2, and E3. So, and we can write the angular velocity omega in terms of components along the principal axes. And so what that would look like is omega is going to be equal to omega 1 E1 hat plus omega 2 E2 hat plus omega 3 E3 hat. Okay. If n hat, oh no. Oh, sorry. I think this software gets frozen and gets slow when there's a lot of notes. Let's try to see if we can get through this. If n hat is equal to cos phi 1 E1 hat plus cos phi 2 E2 hat plus cos phi 3 E3 hat is along the direction of omega, then what we might ask is, what is the rotational inertia in that direction? And so as we wrote down at the beginning, the way that we can calculate that is n hat dot I dot n hat. And so let's just try this for our diagonal rotational inertia tensor. So we're going to have a row vector with the components of n hat. And then we're going to have a diagonal square matrix. And we would have a column vector. Oh. So what I may do in the future is maybe instead of trying to do a long 75-minute class or lecture, maybe I'll do shorter 50-minute ones. And so instead of 2 videos a week, they'll be 3. Something like that. cos phi 1, cos phi 2, cos phi 3 are the components of our column vector. So we'll do the multiplication of the square matrix and the column vector, and we'd get I1 cos phi 1. And then we'd get 0 plus 0. And so that's quite simple. And then for the second one, we'd get I2 cos phi 2. And the third one, we'd get I3 cos phi 3. And then when we multiply the row and the column, we're going to get I1 cos squared phi 1. I may just give it one more try, and then I might just stop this video here. I don't think this is entirely just my incompetence. I think it's the software. So we're going to get an I1 cos squared phi 1 plus I2 cos squared phi 2 plus I3 cos squared phi 3. Okay, now if you look back to when we were first deriving the rotational inertia tensor, we also did a calculation like this, but we included the possibility of off-diagonal terms in our rotational matrix, rotational inertia tensor. And the expression that we ended up with turned out to be really complicated. So what's nice about this is that there are no terms like, if you look back, we would have had terms like 2ixy cos phi 1 cos phi 2, where this ixy, if you like, is the same thing as I12. And then in addition, there would be terms with like the I13 and the I23. And so these components, I12, I13, and I23, were called the products of inertia. So there's no terms like this involving the products of inertia. Which were I12, I13, I23. Okay, now if we wanted to, we could also try to calculate angular momentum. So what about angular momentum? L is equal to I dot omega. Okay, well, for a diagonal rotational inertia, we would have just those non-zero components on the diagonals. And then in terms of components along the directions of the principal axes, we would write omega 1, omega 2, and omega 3 for our column vector. And if we did this matrix multiplication, we again end up with a relatively simple result, which we could express in vector notation. Oh, this thing froze again. Okay, here we go. Are we back? Maybe. It's not so responsive. Or L is equal to I1 omega 1 E1 hat plus I2 omega 2 E2 hat Okay, this froze again, so what I'm going to do is I'm going to stop this here, and then we'll pick it up from this point next time. All right, thanks. Bye.